Chapter 7 focuses on collisions, momentum, inelastic and elastic collisions, and also center of mass. So we're going to do a fair number of problems for this chapter to make sure we go through all different kinds of examples. The first question is just on momentum. What's the magnitude of the momentum of a 10,000 kilogram truck whose speed is 12.0 meters per second? And so momentum, P, is equal to mass times velocity. The mass is 10,000 kilograms. Velocity is 12 meters per second. Okay, so the answer is just 12 times 10, 120,000 kilogram meters per second is the unit for momentum. Okay, so answer for A is just that. Answer for B, what speed would a 2,000 kilogram vehicle have to have in order to have the same momentum? So we know our P is equal to 120,000. We know our mass is 2,000 kilograms, and we want to know what's V. Okay, so V is equal to P over M, just rearranging the equation. So 120,000 divided by 2,000. So that would be 60 meters per second. That's really fast. That's something like 180 miles per hour. Right, part C, how much would it have to have the same kinetic energy as the truck? So kinetic energy is 1/2 mv squared. So for the kinetic energy for the truck is 1/2 times the mass of the truck, 10,000, times the speed of the truck squared. Okay, so we can calculate that. We get 720,000. Unit is joules for energy. So kinetic energy for the SUV has to be equal to the same as the truck, so 720,000, and that's equal to 1/2 times the mass of the SUV times the speed of the SUV squared is equal to 720,000. Okay, so V squared is equal to 2 times 720,000 divided by the mass of the SUV. And the mass of the SUV is 2,000 kilograms. Okay, so we get 720 is V squared. So V is equal to square root of 720, or 26.8 meters per second. Okay, so that's a pretty basic problem, just using the definitions of momentum and kinetic energy. Now let's go on and talk about a collision. So in this case, I've got a collision between a baseball and a baseball bat. And I'm told the mass of my baseball is 0.145 kilograms. And I'm told in part A, I've got a ball that comes in at 45 meters per second and gets batted out at 55 meters per second in the opposite direction. So I've got my ball comes in at 40, goes back out at 55. So it comes in at 45, goes back out at 55. What's the magnitude of the change in momentum imparted by the bat? Okay, so change in momentum is final momentum, the mass times V final, minus the initial momentum, mass times V initial, or that's just mass times the change in velocity, V final minus V initial. Okay. So V final is 55 meters per second. V initial, now V initial is going to the left, so I've got to write that as minus 45 meters per second. So my change in momentum is my mass, 0.145 kilograms, times 55 minus negative 45. So that's going to add up to 100. Okay, so I get 14.5 kilogram meters per second is my change in momentum. If you hadn't been careful about the direction, you would have written down V initial as 45. You would have got a change in speed of 10 meters per second rather than 100 meters per second and then you would have got the wrong answer. So be careful. If you've got a ball coming in and going out in the opposite direction, then the change in momentum is not just the difference between the two speeds. You've got to put the directions in there. Okay, so part B, so that's the answer for part A. Part B says that the ball and the bat are in contact for 2.00 milliseconds. So delta T is 2.00 milliseconds. What's the magnitude of the average force applied by the bat? Okay, well, what we know is in a collision, the average force times the time of the collision is equal to the change in momentum. So we know the change in momentum from part A. We know the time, so we can figure out the average force is just the change in momentum divided by a change in time. So 14.5 kilogram meters per second divided by 2.00 milliseconds, so times 10 to the minus 3. And I get 7,250, and the units for force are newtons. Okay, so again, pretty straightforward. The only tricky thing is to throw in your directions properly. Okay, third question. Now I'm talking about conservation of momentum. Okay, so conservation momentum means the initial momentum is equal to the final momentum. So I've got an astronaut doing work on the space station. So presumably she's stationary beside the space station doing the work. She then throws a tool away from her, and that's going to cause her to move in the opposite direction. Why? Because we know P initial is equal to 0. Okay, so she and the tool are stationary, at least with respect to the space station. With respect to the Earth, they're probably whizzing around at a very high speed. Okay. So P final is going to be the mass of the astronaut times the speed of the astronaut plus the mass of the tool times the speed of the tool. All right, they give us the masses, they give us the speed of the tool, and we need to find the speed of the astronaut. Now, from conservation momentum, we know that the final momentum has to be equal to the same as the initial momentum, which is 0. And so what's the speed of the astronaut? Let's rearrange this to solve it. So MAVA then is equal to minus MTVT, where T stands for tool. And it's negative because I took it over to the other side. So minus MTVT over MA is the speed of the astronaut. Okay, so now we just put in our numbers. Mass of the tool is 2.25 kilograms. The speed of the tool is 3.20 meters per second. The mass of the astronaut is 68.5 kilograms. And so we get the speed of the astronaut is negative 0.105 meters per second. You notice in all these problems I'm given 3 significant figures, so I'm keeping 3 in the answer. Okay. So with what speed and what direction will she begin to move? Well, the speed is 0.105 meters per second. The direction, well, the direction is opposite to the tool. So the tool moves one way, she moves the other way. Okay, fourth question. Again, conservation momentum question. 2 skaters collide and grab onto each other on frictionless ice. So what we have initially is 2 skaters, call them skater 1 and skater 2. They're coming towards each other. They hit each other, and then after the collision, they grab onto each other. So they move off as one object, and I'm not sure yet which direction they're going to move. I'm going to have to figure that out. Okay, so I want to know what's the magnitude of the speed after the collision and what's the direction. So we're told that before, so we'll call this initial and this final. Remember, if the 2 things stick together after the collision, that's a completely inelastic collision. So the only thing we have conserved here is momentum. So the initial momentum has to equal to the final momentum. That's true for every collision. Okay. Now we're told skater 1 has a mass of 70.0 kilograms, and they're moving to the right. V1 initial is 2.00 meters per second. Before the collision, we've got skater 2, 65 kilograms, moving to the left with an initial speed of 2.50 meters per second. Now again, remember, we have to be careful about direction. Since he's going in the opposite direction, we'll throw in a negative sign. Alright, so that's their initial mass and velocity. So we can get the initial momentum is going to be m1 v1 initial plus m2 v2 initial. So that's going to be 70 times 2 plus 65 times minus 2.5. And I get negative 22.5 units kilogram meters per second. Okay, so that tells me that the initial momentum is in that direction, and that means the final momentum is also going to be in the same direction. So after the collision, they're going to go off backwards towards the left. Alright, but let's figure that out, see if we can use our equations to get the answer. Okay, so what's the final momentum? Well, the final momentum has to be equal to the initial momentum, and after the collision, since they're both stuck together, we've got a joint object with a total mass of m1 plus m2 moving with the speed of v2 final, and since that's equal to p initial, it has to be equal to minus 22.5 kilogram meters per second, since we know that p initial equals p final. So v2 final then is p final over the total mass, which is 70 plus 65, and I get negative 0.17, actually I should keep three significant figures, negative 0.167 meters per second. So the magnitude is 0.167. Meters per second, and the direction, because it's negative, is to the left. Okay, this next problem involves an elastic collision. So what we have is we've got an air track glider moving to the right at 0.80 meters per second. It has a mass of 0.15 kilograms. We have another air track glider with a mass of 0.3 kilograms that's moving to the left at 2.20 meters per second. What we want to do is we want to find the magnitude and direction of the final velocities of each glider if it's an elastic collision. Okay, so this is our initial condition. We want to know what's the final conditions for each of the gliders. So the equation that I'm going to use is the equations for elastic collisions. These are not given in your book. Okay, but we've got V1 final is equal to mass 1 minus mass 2 over mass 1 plus mass 2 times V1 initial plus 2 mass 2 over mass 1 plus mass 2 times V2 initial. Okay, so this is the equation that you'd be given on a test you wouldn't expect to remember. Okay, so I want to find V1 final. All I have to do is plug in my numbers. Okay, so mass 1 is 0.15 kilograms. Mass 2 is 0.30 kilograms. V1 initial is 0.80 meters per second, and V2 initial is 2.20 meters per second, and it's going to the left, so I'm going to put a negative sign in front of it. Remember, it's very important to get that right. Okay, so just throw in our numbers. So mass 1 minus mass 2, 0.15 minus 0.3 over 0.15 plus 0.3 times 0.8 plus 2 times mass 2, 0.3 over 0.15 plus 0.3 times negative 2.20. Okay, plug that all into the calculator. and I get negative 0.267 minus 2.933, and I get negative 3.2 meters per second. Okay, so the first glider goes backwards to the left at negative 3.2. How about the second glider? Our equation for the second glider, now I just reverse the things that I had on each side. So plus this, and again plug in my numbers. So I've got 2 times mass 1, 2 times 0.15 over mass 1 plus mass 2 times V1 initial, 0.8, plus mass 2 minus mass 1, so 0.3 minus 0.15 over the total mass times negative 2.20. Okay, so this time I'm going to get a positive number and a negative number. So I get plus 0.533 minus 0.733. So I get negative 0.200 meters per second. So after the collision, what's happened is that the light glider is given a fast speed going backwards, and the heavy glider has slowed down a lot because of the collision, and it's only going at 0.2 meters per second. Okay, the last topic in the chapter is on center of mass. So in this problem we've got 3 objects, A, B, and C, and we're given their masses and their locations, and we're asked to find the center of mass of the system. So first of all, let's draw a picture of what we have. We've got particle A is at 0.2 in the x direction, 0.3 in the y direction. So let's go 2 over and 3 across. There's A. Particle B is at 1 in the x and minus 4 in the y. So there's B. And particle C is at minus 3 in x and plus 6 in y. So minus 3 plus 6, there's C. Alright, so our equation is, what's the x position for the center of mass? It's mass of A times x of A plus mass of B times the x position of particle B plus the mass of C times x position particle C over the total mass of the system. So mass A plus B plus C. So if we put in our numbers into the equation, mass of A is 0.3, its x position is 0.2. Mass of B is 0.4, its position is 0.1. And mass of C is 0.2, and its position is negative 0.3. Total mass is 0.3 plus 0.4 plus 0.2. Okay, so on top we've got 0.04. On the bottom we've got total mass of 0.9. So I get my x position is plus 0.044, and I should keep 3 significant figures, 0.0444 meters. Y center of mass is the mass times the y position for each particle Okay, so that's 0.3 times 0.3 now. A is at 0.3 kilograms at 0.3 meters. For B, it's 0.4 kilograms at negative 0.4 meters. And C is 0.2 kilograms at plus 0.6 meters. And again, I got my total mass, add up all the masses there. Alright, so on the top I've got 0.05. On the bottom I've got 0.9. and I get 0.0556 meters. So the center mass of the system is a little bit less than half in X, a little bit less than half in Y, so the center mass of the system is right where I've got my X there. Okay, and that looks about right. That's sort of, if you eyeball it, it looks like it's about the center of the system. Make sure you're able to do a problem like this. This is a typical center mass problem to find on a test.